limitations, and the constant of integration. Okay, so let's move on to a really important aspect of integration by parts. Now, in the sections we've just covered, we've seen how powerful the integration by parts formula can be, how it allows us to tackle integrals that might otherwise seem impossible. But, and this is a big but, just like any tool in mathematics or even in life, it's not a magic bullet. It has its limits. It's crucial to understand when this method won't work and to be aware of the specific rules we need to follow when we are using it. This tutorial, specifically, is going to address those limitations. We'll look at examples of integrals where integration by parts just isn't the right approach. And, importantly, we'll clarify exactly how to handle the constant of integration, that little plus c we add at the end, to avoid common mistakes. We'll be building on what we've already learned about IBP, and this understanding will be key as we move forward to more complex integration techniques. The scope and limitations of integration by parts. As we discussed briefly on the previous slide, integration by parts is a powerful technique, but it's not a magic bullet. Essentially, it's a method we use to tackle integrals, those reverse derivatives, that are formed by the product of two functions. The goal is to transform a complicated integral into something much simpler that we can solve. Now let's look at the core formula. It's written as integral of f of x times g of x with respect to x equals f of x times the integral of g of x with respect to x minus the integral of f prime of x times the integral of g of x with respect to x with respect to x. Let's break that down. F of x and g of x are simply the two functions we're multiplying inside the integral. F prime of x represents the derivative of f of x, and remember, the integral sign, with the function inside, represents the antiderivative of that function. The key to understanding whether this method will work lies in that second integral, the one we subtract. This is where we need to be careful. The success of integration by parts completely depends on whether that second integral of f prime of x times the integral of g of x with respect to x, is actually easier to solve than the original integral we started with. Think of it like this: we're trading one integral for another. If the new integral is just as hard or even harder, then we haven't really gained anything. In that case, integration by parts isn't the right tool for the job. We'll see an example of this on the next slide, where we'll look at an integral that just doesn't play nicely with this method. So remember, simplification is the name of the game here. If it doesn't simplify, don't force it. Okay, so let's move on to slide 2, where we'll really dig into how integration by parts works, and importantly, when it doesn't. Example of a limitation: \\int \sqrtx \sin x dx \. Okay, so we've discussed how integration by parts works, and now we need to understand when it doesn't work. Just because you can apply a formula doesn't mean it will actually help you solve the problem. This slide illustrates that point. Let's examine why some integrals cannot be solved using this method. Consider the integral of square root of x times sine of x with respect to x. Now, before we jump into applying the formula, let's think about the first step, selecting our functions, f of x and g of x. Remember from our previous discussions, we have a little priority guide to help us make this choice. We generally want to choose the function that, when differentiated, becomes simpler. Following those general guidelines, polynomial, logarithmic, algebraic, trigonometric, exponential, we choose the algebraic function as our first function, f of x in this case. That's the square root of x. We can rewrite that as x to the power of 1/2. So f of x equals square root of x, which is the same as x to the power of 1/2. Then that leaves us with sine of x as our second function, g of x, so g of x equals sine of x. We've made our initial choices. In the next slide, we'll actually apply the integration by parts formula with these selections and see if it leads us to a simpler integral. Remember, the key is simplification. If it doesn't get simpler, IBP isn't the right tool for this job. Applying the integration by parts formula. First, let's recall some basic integration and differentiation rules. We know that the integral of sine x with respect to x is negative cosine x, and if we differentiate x to the power of 1/2, which is the same as the square root of x, with respect to x, we get 1/2 times x to the power of negative 1/2. Now we'll substitute these into our integration by parts formula. Remember, the formula is integral of f x g x dx equals f x times integral of g x dx minus integral of f prime of x times integral of g x dx. In our case, we chose f x to be the square root of x and g x to be sine x, so, applying the formula, we get the integral of square root of x times sine x dx equals square root of x multiplied by negative cosine x, minus the integral of, and this is where it gets a little tricky with the signs, 1/2 times x to the power of negative 1/2, multiplied by negative cosine x, with respect to dx. Simplifying that a bit, we have integral of square root of x times sine x dx equals negative square root of x times cosine x, plus 1/2 times the integral of cosine x divided by the square root of x, with respect to dx. Okay, so let's move on to applying the integration by parts formula to our example, which, remember, is the integral of square root of x times sine x. With respect to x, notice how we've transformed the original integral. But, as we'll see on the next slide, this new integral isn't necessarily easier to solve than the one we started with. That's a key point to remember about integration by parts. It doesn't always lead to a solution, and we need to be able to recognize when that's the case. Analysis of the result. Okay, let's analyze what we've got after applying integration by parts to the integral of square root of x times sine x now. Look closely at the integral we obtained after the first application of the formula. Integral of cosine x divided by square root of x with respect to x. Compare this new integral with the original integral, which was integral of square root of x times sine x with respect to x. Do you notice anything? The new integral isn't any easier to solve than the one we started with. We still have a product of an algebraic function, in this case, 1 over square root of x, and a trigonometric function, cosine x. As we discussed earlier, integration by parts is meant to simplify the integral, and this hasn't happened. In fact, it's arguably more complicated. This means we've hit a limitation of the method. We can't repeatedly apply integration by parts and expect to get a solution using standard integration techniques. Therefore, the conclusion is that, since the process doesn't lead to a simpler form, integration by parts is not a viable solution for this specific integral. It doesn't mean the integral can't be solved, just that integration by parts won't get us there. We might need to explore other integration techniques, or it might be an integral that doesn't have a closed-form solution expressible in elementary functions. Remember, it's crucial to recognize when a method isn't working. Don't force it. As we'll see on the next slide, avoiding common pitfalls like this is key to successful integration. The constant of integration, \c\. Okay, so let's move on to a really common sticking point for students when we're using integration by parts. As we've seen in the previous slides, the integration by parts formula can seem a little complicated with all those integral signs. A frequent question arises: do we add the constant of integration, c, every single time we encounter an integral sign within the formula? Now, let's establish the standard convention. When you're calculating the integral of the second function, that's the g of x function inside the integration by parts formula, we do not include the constant of integration. That is, when you evaluate the integral of g, x, just find the antiderivative without adding plus c at that stage. We reserve adding the constant of integration, c, until the very end of the entire integration by parts process. So, after you've applied the formula, simplified as much as possible, and arrived at your final answer, then you add plus c. We'll explore why this is the case on the next slide, using a helpful analogy to make it clearer. But for now, remember this rule: no plus c during the intermediate integration of g of x, only at the very end. This will save you a lot of unnecessary algebra and potential errors. Why is this done? The logic. Now, to really understand why we handle C the way we do, let's think about a real-world analogy. Imagine you're cooking a multi-step recipe, let's say a stew. If you're making a stew, you don't add the final garnish. Think of that as our constant to every single ingredient as you chop them, right? You wouldn't sprinkle parsley on each carrot and potato individually. You add the garnish only once, at the very end, after the entire dish is fully cooked and assembled. The same logic applies to integration by parts. We don't need to add a constant of integration after every integral we calculate within the IBP formula. Let's look at the mathematical reasoning. Suppose, just for the sake of argument, that we did add a constant, let's call it C1, during the first integration within the integration by parts formula. So, instead of simply integrating g of x, we'd have the integral of g of x plus C1. If we plug that into our integration by parts formula, it would look like this. The integral of f of x times g of x dx equals f of x times the integral of g of x dx plus C1, minus the integral of f prime of x times the integral of g of x dx plus C1 dx. Notice what happens when we distribute that C1 into the second integral. It creates an additional term, the integral of f prime of x times C1 dx. But what does that integral simplify to? Well, since C1 is just a constant, the integral of a constant times f prime of x is simply the constant itself. So, it just simplifies back into a constant. Therefore, since all these intermediate constants, the C1s we'd add at each step, eventually merge into one single constant at the very end of the problem, adding them at every step is completely unnecessary. We call that superfluous, and it just complicates the algebra. That's why we only add the constant of integration, C, once, at the very end of the entire integration by parts process. Okay, so let's tackle a common point of confusion with integration by parts, the constant of integration. As we've seen in the previous slides, sometimes IBP doesn't lead to a solution, and even when it does, handling the constant, C, correctly is crucial. Keep this in mind as we move forward, because avoiding this mistake will save you a lot of headache when you're solving these problems. And remember, as we'll discuss on the next slide, there are other common pitfalls to watch out for as well. Common mistakes to avoid. Okay, let's move on to slide 8. This slide highlights some common mistakes students make when tackling integration by parts, and avoiding these will significantly improve your success. 1. Forcing the method. Now, a very common error, especially when you're first learning IBP, is trying to force the method onto every integral that involves a product of two functions. Just because you can apply the formula doesn't mean you should. Remember from our earlier example with the integral of square root of x times sine of x, we saw that applying IBP actually made the integral more complicated. So before you dive in, always ask yourself, will this actually simplify the integral? If, as you work through the steps, you find yourself going in circles and the integral is just getting more complex, then stop. Reconsider if integration by parts is the right approach for that particular problem. There might be a simpler technique available. 2. Overcomplicating with constants. This is a really important one we discussed in detail on the previous slide. Don't add a constant of integration, plus C, after every integral you calculate within the integration by parts formula. Specifically, when you're finding the integral of g of x, we established that adding the constant at each intermediate step is unnecessary and creates algebraic clutter. Remember the cooking analogy. You don't garnish every single ingredient, you garnish the finished dish. We only add the plus C at the very end after you've completed the entire integration process. 3. Incorrect function choice. Finally, choosing the functions f of x and g of x poorly can completely derail your attempt to solve the integral. It can make an integral that is solvable with IBP appear impossible. To avoid this, always follow the priority guidelines we've talked about. Think of it as a hierarchy. Generally, you want to choose the function that is a polynomial as your f of x first. Then, if there isn't a polynomial, look for a natural logarithm. After that, algebraic functions like square roots, then trigonometric functions like sine and cosine, and finally, exponential functions. Following this order will often lead you to the correct choice and a solvable integral. So, keep these 3 common mistakes in mind as you practice, and you'll be well on your way to mastering integration by parts. On the next slide, we'll wrap everything up with a quick review of the key takeaways. Key takeaways. First point, not a universal tool. Integration by parts only works if the resulting integral is simpler than the original. Remember, integration by parts isn't a magic bullet. It's a technique designed to simplify integrals. If applying the formula makes the integral more complicated or doesn't really change its difficulty, then it's not the right approach for that particular problem. We saw this firsthand with our example, so it's crucial to assess before diving in. Next, ineffective cases. Integrals like integral of square root of x times sine of x dx cannot be solved via IBP because the process does not simplify the integrand. Let's break that down. We specifically looked at the integral of x to the power of 1/2 times sine of x with respect to dx. After applying integration by parts, we ended up with another integral, the integral of cosine of x divided by square root of x with respect to dx, and that new integral was just as tricky as the one we started with. Because it didn't become simpler, IBP wasn't a useful method in that case. It doesn't mean there isn't a solution, just that IBP won't get us there. Finally, and this is a really common mistake students make, constant of integration. The constant c is omitted during the intermediate integration of g of x and is added only once at the final step of the problem. Remember how, when we find an indefinite integral, we always add a constant of integration, c. Well, within the integration by parts process, when you're finding the integral of g of x, you don't add c at that stage. We hold off on adding c until we've completed the entire integration by parts calculation. Think of it like that cooking analogy we used. You don't garnish every single ingredient, you garnish the finished dish. Adding c at each intermediate step just creates unnecessary complexity and will eventually cancel out anyway. Okay, let's recap what we've learned about integration by parts. This slide summarizes the key takeaways, so pay close attention. So, to reiterate, always check if IBP will actually simplify the integral, recognize when it won't work, and remember the rule about the constant of integration. Save it for the very end.